So question 4 from the Mechanics paper Level 2 Physics, the shot put. Hamish is competing in the shot put. This involves throwing a 5.4 kg iron ball, which is the shot, as far as possible. The shot starts from rest and accelerates for 0.25 seconds. Calculate the average force that Hamish exerts on the shot if it leaves his hand at 11 meters per second. Okay, this could be a wee bit confusing, but it basically comes back to this, F equals ma. And we know the acceleration is the change in velocity over the change in time. So we could rewrite F equals ma as F equals m times change in velocity divided by the time, change in time. So all of these factors, 5.4 kilograms, 5.4 not 54, times by the change in velocity, which goes from rest and accelerates to 11 meters per second, so 11 is the change in velocity, divided by the time 0.25 seconds. And when you calculate that all out, you end up with let's see, 240 newtons. Okay, and that's for two significant figures, because all of the other information is two significant figures. Next part, when the shot lands, it rolls around the ground at 1.5 meters per second and collides head-on with a stationary shot which has a mass of 4 kilograms. This is sounding awfully suspiciously like a momentum type of question, collisions and maybe some vectors thrown in. So, collides head-on with stationary shot, has a mass of 4 kilograms. The friction force is negligible during the collision. After the collision, the 4 kg shot rolls forward at 2.4 meters per second in the same direction that the 5.4 kilogram shot was initially rolling. Without doing any calculations, what can you say about the total momentum and the momentum of 4 kg shot during the collision? Okay, well, discuss your answer. The total momentum, okay, according to conservation laws, the total momentum is always conserved. Total P is always conserved. There we go, so that's the main thing. Then when we look at the momentum of the 4 kilogram shot, by itself, its initial momentum is 0 because its initial velocity is 0. This is for the 4 kg. And then after the collision, the 4 kg shot is rolling forward at 2.4 meters per second. So the final momentum is the mass of it, 4.0, times by the velocity, which is 2.4, which gives us, what's that, 9 point something, 9.6, is that right? Doesn't matter anyway, but it's definitely something. Okay, you could calculate that out. What else do we have? We can use this information to work out whether that initial shot will also continue rolling or not. But I guess the essential parts of this is that total momentum is conserved, and that some of the momentum of the 5.4 kg shot is transferred to the 4 kg shot. How do we know that? Well, we're assuming a little bit. We're told that the friction force is negligible, so with the total momentum being conserved, we're assuming there's no forces acting on it. That's the discuss your answer part, because you can give an answer, but now you need to give a bit of detail. So look out for clues like that when it says discuss or explain a little bit more. So there's no forces acting on it, so the momentum's conserved. And what was the other part? Discussing our momentum increase, we would say that there's some momentum lost from the 5 kg, momentum lost from the 5.4 kg and goes to the 4.0 kg instead. Okay, that's good enough. Disappointed there weren't vectors, but there might be here. C. We've got the initial conditions and the final conditions, so before the collision here and after the collision here. And we're to calculate the velocity, which is the size and direction, we should know that anyway because velocity is a vector, of the 4.5 kg shot after the collision. Okay, so this is actually going into what I mentioned a little bit before. We have to find the final velocity. Oops, we need to keep that on the screen. We've got the initial velocity of this part is 0, but we don't know the final velocity of this part. Okay, so we have to calculate that velocity. We know that the total momentum initial equals the total momentum final in the after. So we can say that 1.5 times by 5.4 is equal to excuse me, equals the total initial momentum, and that should equal, let's see, I'm going to have to do this below, for the final conditions it should equal the final velocity times by 5.4 of the 1 plus the 2.4 times by the 4, which is the momentum of the second. So basically we're adding these two momentums here, 1 and 2, and we're seeing if they match with the initial conditions over here, the total initial momentum, because we might know momentum's conserved. So this equation, using this section here, we can calculate it out. So 1.5 times 5.4 should equal VF times 5.4 plus 2.4 times 4.0. When we rearrange all of that, because it's just one equation with one unknown, our one unknown is our final velocity here, we'll find that final velocity equals 0.28 meters per second. Yeah. Now, a little bit of the trick though is that it's actually going to be moving in this direction. How do we know that? We've got to take it'll come out negative essentially. So just to make that a little bit clearer, so that you don't lose what's going on, we've got that 1.5 times 5.4 equals 5.4 times Vf, that's the velocity we're looking for, plus 2.4 times 4.0. So we add up, well, this section here we're going to have to take away from this section, so we end up, when we do that, we end up with negative 1.5 equals 5.4 Vf. So then Vf is going to be negative 1.5 divided by 5.4, which actually gives us negative 0.28, or 2777 recurring, but negative 0.28 meters per second. The negative just indicates that it's bouncing back in that way. Okay, and I think that might be all the questions for this part.